Hey there, welcome back. We are here for part three of our chapter four series on force. This particular video here is going to focus on some of the math and actually taking a look at solving some math problems that have to do with either calculating force, calculating acceleration, I guess could be calculating velocity, those sorts of things, having to do with motion systems that involve force or applications of force, et cetera. So with this, I wanted to kind of start off with a little brief reminder on some of the problem solving strategies as we start to move into more complicated types of systems. It becomes really important to kind of focus on those basics yet again. So I've kind of got them on here on the screen again, just to sort of remind you of the things that we're going to do. And I'll try to model these today as I'm going through and doing these problems. But it's really important to make sure that you're always sketching the problem, drawing those free body, those force diagrams. You know, it doesn't have to be anything fancy, but you really should be identifying where your forces are, because it can sometimes help with either identifying hidden forces or missing variables. And a big one is to identify directions. So making sure that you're identifying which way is positive, which way is negative, left, right, up, down, et cetera. Because in these sorts of problems, they're not going to identify a force as being negative 20 newtons. They're going to say 20 newtons to the left or 20 newtons to the right. So kind of important to make sure that you're in there. It's also important to make sure that we're talking about net forces, and drawing that force body diagram helps you identify which pairs of forces are actually going the same direction. When we're combining forces, you're only combining forces that are in the same plane. So either both X forces or both Y forces, but you don't combine X and Y, not yet. That's chapter 5. The last two things are hints about, or three things, I guess, are hints about some of our Newton's laws. So keep in mind if they talk about constant velocity, if there's some sort of a hint in there about the speed of something not changing, make sure then you know that your net forces, your left forces versus your right forces, are equal and opposite. They add up to 0. If you've got any sort of acceleration, however, you know that your net forces are not equal to 0, and you're probably solving for that, trying to figure out what your net forces are, or you're applying net force to figure out what your acceleration is. So again, you've got to kind of take a look at those two things. That hint is sometimes that's in there. And then the last one is to keep an eye out for the term weight versus mass. Because that does play a difference here. And a lot of students, especially first-time physics students, they miss that concept that weight is actually a force. It's Fg, and that it's due to mass times 9.81. And so that's one of the things that, again, a lot of first-time physics students, hopefully there aren't that many first or second-time physics students, but that's one of the things that happens a lot. So again, keep in mind that if you're talking about mass, you're talking about kilograms. If you're talking about weight, this is in newtons. And again, if you want to figure out what something's weight is, Fg equals m times g, where g is acceleration due to gravity. So they're directly related to one another, but they are a little bit different. And so you want to be really paying close attention to your units or other things like that that might give you hints as what you're up to. So the rest of this is going to be some example problems of how we apply different types of Newton systems to things. You probably want to have your calculator, scratch paper, etc. This is one of those videos where it's definitely more helpful for you that, I introduce the problem, hit pause, see if you can sketch it out, kind of follow along. It definitely works better for you. You get more out of it that way, but you do you, right? So example number 1 is an example of Newton's first law, believe it or not. Objects at rest tend to stay at rest. Objects in motion tend to stay at motion until acted upon by an outside unbalanced force. This is called terminal velocity, the fact where your downward forces and your upward forces end up canceling one another out. So you've got a person with a mass of 70 kilograms. They achieve terminal velocity. What's the force of air resistance on this person? So if you have a person, you've got a couple of different forces. Number 1, there's a downwards force. That's F of G, the weight of the person. And then there's an upwards force. And in this particular case, it's going to be a force of like air resistance, FAR or something like that, whatever you want to call it. But your air resistance force is pushing up on that person. Notice when I draw these, I oftentimes draw them so that they're kind of emanating from the center of the same thing. It doesn't really matter a whole lot. It just have to kind of be careful to make sure that they're kind of identifying how they're acting on there. So FG would be pulling downwards. It's the weight of the person. That's the force of gravity that's pulling that person to Earth. And then the force of the air resistance, and again, you could draw it up from down here, is what's sort of fighting that. So with this, there's my free body diagram. I know a few things now. Because they've achieved terminal velocity, Terminal velocity means they're going constant speed. So that means that my net force is equal to 0. They add up to or balance each other out, however you want to say that. I'm going to say that my up direction, by the way, I'm going to call it this way, is positive, just to kind of use my typical kind of directionals. So I know my net force is positive. So that means that I know that F of my air resistance and my F of G have to be equal and opposite to one another. So that's what I can kind of take a moment of trying to figure what that out is. So we're trying to figure out what air resistance is. AR is going to be our unknown. How about FG? What is that? Well, as I said earlier, FG equals M times G. So we know now that our net force is equal to 0, which equals our force of our air resistance, FAR, plus F of G. So now what is this? Well, our mass is 70.0 kilograms. Again, kilograms is our standard unit of mass. And our acceleration here is negative 9.81 meters per second squared. Again, I have to put that negative sign in there because it's downwards. That's why I'm giving it that negative sign. So 70 times 9.81 negative is going to be equal to 0 equals FAR minus 686.7, and this is now newtons because that's a force at this point. That's that person's weight. So that means that the force of air resistance has to be equal to 686.7. Looks like 3 sig figs, 687 newtons equals FAR, and that would indeed be positive because that's upwards, right? So if its weight is downwards, air resistance is pointing upwards, and there you've got terminal velocity. So that's the air resistance on that person, 687 newtons. It depends on how heavy the person is, right? Okay, problem number 2 has to do with an acceleration problem. Now, that first one was about net force is equal to 0. This one, we've got acceleration present here. So we've got a grocery bag weighing 3 kilograms, accelerated upwards by a force of 17 newtons. How fast does the bag accelerate? So this is Newton's second law. Newton's second law says net force equals mass times acceleration. Okay, so what do we got? So we have an upwards force of 17 newtons. We've got our bag right here. There it is, right? It's got F of G right here. It's going to be pulling downwards. And then it also has an upwards force. So maybe this is our FA, right? We know that this one is 17 newtons. So we want to figure out what our net force is to figure out what our mass times acceleration is. Remember, our net force is F of A plus F of G. Now, knowing that one of those is up and one of those is down is kind of the important part here. So, all right, what are we trying to find? Well, our applied force is 17. We've got that. We know what this is. We can figure out what FG is, and we know what mass is. So now we can start plugging things in. So we're trying to figure out our net force, and I don't even know what that is yet. It doesn't really matter a whole lot. I know what mass is, 3 kilograms. This is kilograms, right? Times my acceleration has to be equal to my applied force. I'm accelerating my bag upwards by 17 newtons. 17 newtons. I'm going to say upwards, my direction is positive, so I'll make that one positive, plus my F of G. Now, what's FG? FG is the weight of the bag, which is 3 kilograms times negative 9.81. Okay, so what is that going to be? 9.81 times 3 kilograms is 29.43. 29.43. So what is this actually equal to? So 3A equals, and this is newtons as well. Oh, by the way, negative 29. Sorry, because it's downwards, right? We got that. So 29.43 minus 17 on the right side gives us negative 12.43. 3A equals negative 12.3. Divided by 3 to solve for A. Acceleration is negative 4.14 and some change, 43333. And this is meters per second squared. Now, what the heck does this mean? All right, how is this possible? If we've got an acceleration of negative 4, we got like 1 or 2 sig figs here, depending on how I want to do it. Acceleration of negative 4.14. What does that mean? That means I'm actually not picking it up. It means I'm actually setting it down. Its acceleration is in the downward direction. Now, how is that possible? You say, okay, well, remember, if you just drop it, you just drop it. It's going to accelerate downwards at negative 9.81 meters per second. But I'm accelerating it upwards by a force of 0.17 newtons. What you would call that is lowering it down, right? I am lifting it against, but I'm setting it down at the same time. Now, I'm not setting it all the way down, right? I'm setting it down gently at about half the speed, half the acceleration that it would have for acceleration due to gravity. So I know it sounds kind of funny to say that. Is that possible to do that? Yeah. If I'm accelerating it upwards at 17 newtons, I'm setting it down. Again, I'm not just letting it fall. I'm sort of helping it down to the ground in a nice way, if that makes any sense. So I'm lifting, but the bag is moving downwards. And that is perfectly acceptable to do that. I get it's kind of a weird situation, but I just want to make sure that you're kind of clear that that is a possible situation to have. So there you go. All right, let's move on. Okay, case number 3. Acceleration, we got a box weighing 3 kilograms is accelerated to the right at 2 meters per second. If the friction between the box and the floor is 4.5 newtons, what was the force needed to move the box? Okay, well, let's take a look at what we got here. We've got a box, right? All right. And it's moving to the right. It's moving this direction. So I'm going to use my squiggly arrow to represent movement. That's not a formal thing. That's just a me thing. That's a Bedwell thing. So here's my box moving to the right. So I'll say this is the positive direction. I know some things about it. I know how much it weighs. F of G is going to be equal to 3 kilograms times 2 times 9.81. I don't know if I'm going to need that or not, but 9.81. Okay, there we go. Negative. And that's going to be downwards, right? I know it's being accelerated to the right at 2 meters per second. So acceleration is this direction at 2 meters per second. And we're going to call that positive 2 meters per second. We know what the bag weighs, or the box weighs. All right. Friction between the box and the floor is 4.5 newtons. Well, if the box is moving to the right, that means friction is actually going this way. Again, if the box is moving this direction on the screen, the friction force, F of little f, is the other way. This is negative 4.5 newtons. We need to know what the force was needed to move the box. So now we're trying to figure out what F of A is. That's what we're trying to find. Okay, so how do we start to attack this? Well, net force equals mass times acceleration. We can figure out what our net force is. I know how much the box weighs, 3 kilograms. I know what my acceleration is. It's accelerating to the right at 2 meters per second. So that means my net force has to be equal to 6 newtons. So we know that much. Okay. So we know that the net force on our box is 6 newtons. We have 2 forces that add up to net force. We also know that net force equals F of F, friction force, plus FA, which is our applied force. So now we know what our net force is. It's got to be 6 newtons. Friction force is negative 4.5 newtons. Why? Because again, it's moving to the right. Friction force is fighting it. It's going to the left. And then we can figure out what our applied force is. So now it's just a matter of solving for what our applied force is. I don't need a calculator for this. Our applied force is 10.5 newtons equals FA. I had to push harder to overcome that force of friction. So my applied force was over 10 newtons because I had to fight 4 newtons of friction force in order to get this thing to accelerate to the right with a net force of like 6 newtons. So again, it makes sense that our number it works, and that should be positive because it's going to the right, friction's going to the left. Sig figs, if we do 1 sig fig, you can call it like 10, whatever, 11 newtons, something along those lines. If you want to round it to sig figs, 10 newtons. There you go, positive would be our answer with 1 sig fig. So again, with this, it's directions, and keeping in mind, did we use FG? No, because our motion was horizontal. That vertical force didn't do anything for us in this particular problem. So yeah, you can figure out what FG is, but in this case, it didn't do much work for us. Again, horizontal motion is what we were looking at, accelerating horizontally. We needed to use our X forces, not our vertical Y forces. All right. Get into a couple of trickier ones here, the last 2. One's apparent weight, and the other one's called bag of trouble is the name of the other one. So apparent weight. I don't know if you've ever been in an elevator before. I'm assuming you have. But you guys know that when you get on an elevator, when the elevator goes up, right, and the elevator's pushing on you, you actually, because of Newton's third law, equal and opposite reactions, you start to feel heavy for just a second, right? The elevator's pushing you, you kind of feel that sag as the elevator's pushing you upwards. Similarly, if you're in an elevator and the elevator's going down, you kind of feel that moment of, whoa, kind of that light weight. So if you want to lose weight, by the way, just get in an elevator. You don't lose mass, but you do lose weight, at least temporarily. So this is called an apparent weight sort of an issue. So you're standing on a scale, you're riding the elevator upwards. So again, the elevator now is moving this direction. We can call that positive if you want to. It's moving up. So you should be reading, this should be heavier, right, than you actually are. Person's mass is 50.1 kilograms. What's the acceleration of the elevator? So one of the things that's important to recognize here is, what is the scale actually reading? So what the scale is actually reading, if you've got a scale that you're sitting on and you're, the person that's sitting here, this is you. That's kind of weird. What a scale actually reads is something called normal force. So hopefully you watched that earlier video about what some of these different forces are. You are pushing down on the scale with F of G. The scale is pushing back up on you with Fn, or F, that's supposed to be an N, right? It's actually reading normal force, but sometimes people just call it F, SP for the spring, or FSC for scale, something along those lines. But that's actually what's kind of trying to figure out for you. It's pushing back up. So under normal situations, right, if we were to put you on the scale and you weighed 50.1 kilograms, then the scale should read your weight, which would be 50.1 times 9.81, right? That's what it should read. It just doesn't do the negative sign. So that's what F of G is. If you're actually measuring your weight, then it should do that. But this is not measuring your weight, right? It's measuring your weight plus. So it's actually measuring this normal force, which is now like, you've got a couple of funky things that are happening because the elevator's moving. You've got this additional sort of acceleration that's happening. So what does this mean? So if the scale is reading 591, that means we've got an upward force of 591, and we have a downward force, right? This is the scale. The downward force is simply you, whatever 50.1 is times 9.81. 50, oops, I could do this right. 50.1 times 9.81. Okay, so downwards is 491.481. So this is our upwards force of our scale. This is our downward force of our gravity. So it's reading extra, right, than what you actually weigh. So now we can combine these two things together to figure out what our net force is. What's working on these? One of these is negative, one of these is positive. So 591 minus 491.481 gives us a net force equal to positive 99.519. That's our net force. Again, it's reading more than it should. We've got some positive upwards force on there that's happening. Again, if you're going down, it would read less than that 491. It'd be kind of weird. So our net force is 99.519. If we have net force, we have mass times acceleration. 99.519 equals 50.1. That's the weight of the person times the acceleration. So now you can just take it, 99.519 divided by 50.1 gives you an acceleration of A equals 3 sig figs 9 meters per second squared equals acceleration. And yes, it's positive because you're accelerating upwards, right? Makes sense. You're heavier than you should be. Elevator has to be moving up, dragging you upwards, so to speak. And again, because of that, it's accelerating up about 2 meters per second. So therefore, your weight has increased. Again, you want to lose some weight, just go down in an elevator, temporarily anyway. Okay, these are a little tricky, right? Okay, so moving on. Bucket of trouble or bag of trouble. These are oftentimes the type of problems that are couched in you're lifting something and you want to know whether or not the object is going to break. Will the rope break? If you guys have ever carried too many groceries in a plastic grocery sack, right? If you lift it up, are the handles going to break? Well, it turns out, again, this is a net force issue. And because it's a net force issue, the acceleration is actually the key. You may have noticed that before, that if you lift up very gently on a plastic bag that's about to break, if you just gently lift it, right, very little acceleration, it can hold. But if you try to jerk your hand up, right? Major acceleration, then all of a sudden that handle will break. So that's kind of what this is related to. Again, these are just kind of colloquial called the bucket of trouble kind of problem. So we've got a 50 kilogram bucket right here, lifted by a rope. You can see our example right here. The rope will not break as long as the tension is less than 525. So this right here is a comparison value for comparing. That's what you're going to ask later. It's kind of like those, hitting the barrier kind of questions. You're probably not going to use this number in your calculation. You're just going to check your answer later and say, hey, is my answer greater than or less than 525 newtons? That's what that comparison value is. So we've got our bucket starting at rest. Okay. And then after being lifted for 3 meters, it's moving at 3 meters per second. Is the rope in danger of breaking? So again, assuming constant acceleration, we need to figure out what is our acceleration is what we're trying to find. And then we got to use that acceleration to figure out what our force is. Again, because force equals mass times acceleration. And that's what we need to try to figure out. All right, so what do we got? How do we figure out acceleration? Right? If I'm trying to do net force equals mass times acceleration, I need to figure out what acceleration is. It looks like kinematics to me. There are a couple problems in your homework that are kinematics problems that you need to be able to use. I did put the answers for the kinematic problems in the homework assignment, but yeah, you do have to go back and look some of those up. So get that sticky note out. We know VI equals 0. We know that D equals 3 meters. And this is actually DF, right? And after those 3 meters, it is moving at 3 meters per second. VF equals 3 meters per second. I don't see time. Ain't got no time for that. We're trying to find A, right? Ain't got no time. Doesn't say how long we're moving it. We're just gently lifting it up. So therefore, we're going to use our equation VF squared equals VI squared plus 2A delta D. Again, how did I get there? I'm trying to figure out the force in my rope, which means I've got mass. I need to find acceleration in order to find force. So I'm kind of working backwards. So here's how I can find acceleration. Why did I pick this equation? Because I ain't got no time for that. If I ain't got no time, this is the equation that we're going to use, right? So I know what my VF squared is. 3 squared equals 0 squared plus 2 times A times delta D, which is 3 meters, right? 2A3. So 9 equals 6A. And A equals whatever that value is, 9 divided by 6, 1.5. I knew that. 1.5 meters per second squared. All right. So now what? Now we know our acceleration is. Acceleration is equal to 1.5. So we know that. All right. Acceleration is equal to pen equals 1.5. Okay, so now I got that. Yay. Got that. I'm going to erase this part just so I have some more room to work. So now I know a few things, right? Okay, so acceleration is equal to 1.5. Well, now what? Now we got to figure out what our net force is, right? Do we have enough? Okay, what's our net force? Okay, net force is going to be mass times acceleration. We know it's accelerating at 1.5. We've got how many kilograms of mass? The 50 kilogram bucket. All right, so let's figure out what we got. 50 kilogram bucket, net force equals 50 kilograms times our acceleration of 1.5. That means our net force is 50 times 1.5 equal to 75 newtons. Okay, so does our rope break or not? Well, it kind of depends on a couple of things, right? So keep in mind what our net force is, right? Our net force here is we've got our bag, we've got FG is going down, we've got FA is going up, right? Let's think about our system here. So net force is the difference between these two, or the sum of them, I guess you want to call it. One's up, one's down. FA plus FG. So we have to take these into account. It's accelerating upwards at a 1.5 meter, so our net force on the bag is 75 newtons. So we do need to know what FA and FG is. Now, FA is that tension in the rope. I'm yanking that rope upwards. Is that going to be bigger or less than 525? Well, we need to figure out what FG is. So we do need to do that. I'm going to erase this part. How do we figure out what FG is? Well, FG is the weight of the bag. 50 times 9.81. So do we know what that is? Well, 50 times 9.81. Okay, the weight of the bag is 490 equals 490.5 newtons. That's Fg, and it's down. So I'm going to make it negative sign. So 75 newtons equals the force on the bag, the lifting force, minus 490.5 newtons again. So Fa is the upwards force, Fg is the downwards force. So what does it have to be? I'm going to solve for that by adding it to 75. So 490 plus 75 is 565 newtons equals Fa. So what the heck does that mean? Well, I'm applying 565 newtons to this bag, or to this bucket. The rope will not break as long as the tension is less than 525, which means that those kids are going to be depressed. We're in trouble. The amount of applied force that we're creating to lift it up at 3 meters per second is greater than the tension in the rope. So the bucket could easily break. How would you fix that? Just accelerate the bucket less. Literally, just don't lift it as fast. Lift it a lot more slowly, a little more gently, and you could probably lift it up. So there you go, bucket of trouble problem. So with all of these, again, the things that you need to remember is if you've got acceleration, you've got net force equals mass times acceleration. So you've got upwards forces and downwards forces, so be careful with that. Make sure that you're left and right forces. So make sure that you're adding those together. Don't forget to take into account the weight of the object, especially if you're lifting things up, which is Fg, which is simply the mass of the object times negative 9.81. And again, make sure that you're following your directional signs. So there you go, a couple of examples of some of our math problems. Do I have one more? I think that was the last one. Yeah, that was the last one. So I hope that helped a little bit. I know it's kind of confusing, right? Clear as mud. You got to kind of start working through these. Drawing your pictures, labeling your variables, looking for those forces, up, down, left, right, pairs of forces, adding them together to get your net force. So there you go. And I will see you guys in class. Have a good one.